Welcome back. In the second part of this lecture, we'll be talking about graphs of logarithmic functions and solving logarithmic equations. To begin with, I'm looking to come up with the basic shape for the graph of a logarithmic function, and I'm going to use that using what I know about exponential functions. So here in this example, I'm going to graph y equals 2 to the power of x, and I'm also going to graph its inverse, which is the log base 2. So I'm just plotting in what I know about exponential functions. In this case, an exponential function with base 2 should pass through the points 1 comma the base, which is 1, 2. It should pass through the y-intercept 0, 1, and should pass through the point negative 1 comma 1 over the base, which is 1/2. There we go. And there's my exponential function graphed. Now, I'm going to do in blue the graph of log base 2. And so the first thing would be, since the exponential function had a horizontal asymptote y equals 0, then my logarithmic function will have a vertical asymptote x equals 0. I'm drawing this in blue just so in case anyone's feeling weird about it looks like something is crossing this vertical asymptote. That's fine here because what's crossing the vertical asymptote is the graph of 2 to the power of x, which doesn't have a vertical asymptote. It's the graph of log base 2 of x that will have a vertical asymptote. So there we go. So I've drawn in my vertical asymptote x equals 0, and now I know that it's going to have all the same points as 2 to the x, just with the coordinates switched. So instead of the point 1, 2, we'll have the point 2, 1. Instead of the point 0, 1, we'll have the point 1, 0. And instead of the point negative 1 comma 1/2, we'll have the point 1/2 comma negative 1. And there we go. This is my graph of log base 2 of x. So a couple of things just to notice here. There's the fact that both of these graphs have asymptotes. Exponential functions have horizontal asymptotes. Logarithmic functions have vertical asymptotes. And also they have 3 nice points. For the exponential, it was 1 comma the base, 0, 1, and negative 1 comma 1 over the base. For the exponential function, for the logarithmic function, it's those points reversed. Base comma 1, 1 comma 0, 1 over the base, comma negative 1. So if we wanted to do this, graphing this logarithmic function using transformations, we now can start off with what we know for our basic shape. Here the basic shape would be log base 3 of x, and I know what that should look like. It should, number 1, have a vertical asymptote, x equals 0. It should pass through the points base comma 1. In this case, the base is 3. So 3, 1, 1, 0, and 1 over the base, comma negative 1. Or in this case, 1/3, negative 1. And there we go. That's log base 3 of x. So that's my basic shape. And now I've got 2 transformations to do. First, I have a shift to the left by 2 units. And then I will vertically stretch by a factor of 4. So shifting left by 2 units. So that's subtracting 2 from every x value. Of course, if I'm shifting things left and right, the vertical asymptote, when I shift it to the left, will also move along with the graph. So that means that not only are my points moving to the left, that vertical line can also be shifted to the left as well. So instead of x being at 0 for the vertical asymptote, it'll be -2. And now I'm just going to shift all of my points to the left by 2. So 3, 1, subtracting 2 from every x value. 1, 1, subtracting 2 from every x value. And then finally, 1/3, -1. If I subtract 2 from that x value, 1/3 minus 2, that's -5/3. And -5/3 is just almost -2. It's -1.6-ish. So again, I'm labeling it with the exact value of -5/3, -1. Oh, I think I'll do that over here. I don't think I've got enough room. Did not leave myself enough room to fit my labels in quite nicely. And I'll need to move that one too. There we go. And now, the only thing left for me to do is just label this. So this is log base 3 of x plus 2. There we go. And then last transformation that I need to do is the vertical stretch by a factor of 4. Vertical stretch will not affect my vertical asymptote. If you're imagining this line and stretching it vertically, it's the same line. So the vertical asymptote will stay where it is, but all of the other y values will all be multiplied by 4. So we'll stretch our graph and it'll be taller than it originally was. So let's graph that. The vertical asymptote still is going to be at -2, so x equals -2. And now we just have our points 1, 1. I multiply its y value by 4 to get me the point 1, 4. We had -1, 0. The y value is 0, so it stays as 0. And you had -5/3, -1. Multiplying the y value by 4 gets me -5/3, -4. And there we go. And that's my graph of 4 log base 3 of x plus 2. All right, so now we want to find the inverse of this. And just again, to circle back, we know that the inverse exists, not just because we keep saying that logs and exponential functions are inverses of each other, although they are, but just thinking in terms of knowing this graph, this is a one-to-one function. This would pass the horizontal line test, so definitely we do have an inverse function. So first off, we had f of x was 4 log base 3 of x plus 2. We would rewrite this as y equals . And then remember, what we do next is to switch the x's and the y's. So we would have x equals 4 log base 3 of y plus 2. And now I'm going to solve for y. I'll first divide everybody by 4. And now I'm going to use what I know, which is that logs and exponential functions are inverses of each other, which means that originally I had log base 3, so the inverse of that should be 3 to the power of, and that we'll be switching our inputs and outputs. For the logarithmic function, x over 4 was the output, so for the exponential function, x over 4 should be my input. Y over 2 was going into my logarithm, so y plus 2 is coming out of my exponential function. So now I've got y plus 2 is equal to 3 to the power of x over 4, or y is equal to 3 to the power of x over 4 minus 2. And there we go. This should be my inverse function. So I can say f inverse should be 3 to the power of x over 4 minus 2. So that's kind of a key idea here, is using an exponential function to solve a logarithmic equation. That we can rewrite something that was logarithmic as something that's exponential, and that can be a way that we'll be able to solve an equation. The one thing that we need to be careful here is, just like how it was for radical equations, where you could wind up with an extraneous solution, it's also true with logarithmic equations that you could wind up with an extraneous solution. And the reason for that is it's similar to what we had when we solved radical equations, that by the process of squaring both sides, you could wind up creating extraneous solutions, because for those even roots, those square roots, the insides would need to be non-negative. Same kind of a thing is going on here. If you have a logarithmic equation, you know that the inside for any logarithm can't be 0 or less. But when you rewrite things as an exponential equation, exponential functions are defined for every x. So it's possible that you could solve a logarithmic equation and come up with finding solutions that actually don't solve the original equation. So one thing that I will say here is that when we're looking to solve a logarithmic equation, it's going to be mandatory. We must check our solutions, because it's possible that one or more of our solutions might be extraneous. Okay, so the first one is going to be the most straightforward one of all. We have log base 5 of x is equal to 4, which as an exponential equation, that would be 5 to the power of, and that we would be switching the inputs and the outputs. X was the input for the logarithm, so x is the output for the exponential function. And 4 was the output for the logarithm, so 4 should be the input for the exponential function. So x is 5 to the power of 4, or in other words, x is 625. And we can check this if we want to. This is one where it's easy enough, and we don't really need to worry too much about this one, because if you're thinking about that value of 5 to the power of 4, and I said on the left side of your equation, what do you have? You would have log base 5 of 5 to the power of 4. And of course, log base 5 of 5 to the power of 4, 5 to what power gives you 5 to the 4? The answer is the power should be 4. And conveniently enough, that is the right side of your equation. So left side and right side are indeed equal. And that's why I felt justified in saying that 625, or 5 to the 4, that is your solution. All right, let's do another one. We have log base 4 of x squared minus x plus 4 is equal to 2. So first off, I can rewrite this as the exponential equation. 4 to the power of 2 equals x squared minus x plus 4, switching the x's and the y's. And then this has just given me a nice little quadratic equation to solve. And we come up with two values of x. X is 4 and x is -3. Now, before I can state that either of those happen to be solutions, I really should check them. So I'm going to check both solutions. And when we check our solutions, we're going to check in the original equation. So that means I'm not going to be taking 4 and putting it into this equation to see if it makes left side and right side equal to each other. I'll be taking 4 and putting it into the original equation and seeing, does it make left side and right side equal to each other? And then I'll do the same thing with -3, asking myself, does it make left side and right side equal to each other? So first off, let's check x being 4. So if we put 4 into the left side of our equation, we would have log base 4 of 4 squared minus 4 plus 4, which is log base 4 of 4 squared. And 4 to what power gives you 4 squared? The answer is the power is 2. And conveniently enough, that is indeed equal to what we have on the right side. So 4 is a solution. Yay. And we can check the same thing out with -3. So the left side, we would have log base 4 of -3 squared minus -3 plus 4, which, if we're calculating that out, that would be 9 plus 3 plus 4, which is 16. So we've got log base 4 of 16, or in other words, 4 to what power gives you 16? And the power is 2, which again, that's the right side of your equation. So left side and right side are equal to each other. So both of these were solutions for our original equation. So both of these are our solutions. The solutions are +4 and -3. All right, let's do one more here. So first off, before I can rewrite this as an exponential equation, I'll need to isolate that log. So first I'm going to bring the -4, bring the 1 over along with it. That gives me -5. I'll divide everybody, both sides, by -5. So now I've isolated my logarithm. I can rewrite it as an exponential equation. And before I do that, reminder that when I say natural log of x minus 3, that's the same thing as log base e of x minus 3. So when I rewrite this as an exponential equation, it will be exponential with base e. So I'll have e to the power of, and then again, we're switching inputs and outputs. And I come up with x is equal to e to the power of 1 plus 3. This might be a place where you feel like you're obliged to run to your calculator and turn this into a decimal, and I would say don't do that. Not only for the reason that we want to have exact values, and your calculator here will only give you decimal values, but you'll run into a problem if you're trying to use a rounded off value for e to the power of 1 plus 3 to check your solutions. So if I used my calculator and said, oh, this is about 5.7, and I tried to put 5.7 into the left side of my equation, I won't get that it's equal to the right side. It'll be close to the right side. But to actually show that the left side and the right side are equal, I would have to use the exact value. And that's not hard for me to do, because if I'm looking to check that solution of x equals to e to the power of 1 plus 3, on the left side of your equation, you'd have 1 minus 5 times natural log of e to the 1 plus 3 minus 3. So here I've replaced the x with e to the 1 plus 3. The plus 3 and the minus 3, those cancel each other out just nicely, leaving me natural log of e to the 1. And if I'm thinking about that, natural log of e to the 1, that's log base e of e to the 1. That's e to what power gives you e to the 1? And the answer is 1. So what I have there, that 1 minus 5 times natural log of e to the 1, natural log of e to the 1 is just 1. And there we go. That is equal to negative 4. And the right side of my equation also was negative 4. So indeed, left side and right side are equal to each other. So that means that my solution set does contain just that single value, e to the 1 plus 3. And again, that would be how you should state your answer, as the exact value, e to the 1 plus 3. If you're to tell me that the answer is 5.7 or 5.71 or even 5.71828, you've done some rounding. Those are all approximate values. None of those are the exact value. The exact value is e to the 1 plus 3. All right, same sort of thing can be used here if we're looking to solve an exponential equation rather than a logarithmic equation. You would solve by first isolating the exponential, which it already is. 10 to the power of x minus 3 equals 7. And then you could rewrite it as a logarithm. In this case, rewriting it as log base 10, or the common logarithm. So you can write the 10 down or not. But what will happen will be, again, same as before, we will switch our inputs and our outputs. So that x should be 3 plus log of 7. This is one where we don't have to check our solutions. Remember that exponential functions are defined for all values of x, so we don't have to worry about extraneous solutions coming up. If you wanted to check your solutions, you certainly can, but you don't have to. One other place, and this is to help you out as far as notation goes, you might have noticed that I put the 3, when I moved it to the other side, I put it at the front, that I didn't write it as log of 7 plus 3. And the reason I didn't do that is because this, as it's currently written, is ambiguous. You might wonder, is the 3 going inside of the logarithm as well, or is it just the 7? This would be a place where if I wanted to write it as log base 7 plus 3, where brackets would be useful, then it would be clear to whoever's reading it that, oh yes, only thing that's going into the logarithm is the 7, and that the 3 is not. But if I didn't have brackets, then it would be unclear whether I really mean that the 3 and 7 are being added first, or whether it's just the 7 going into the logarithm and the 3 is a separate thing. So for me to prevent that sort of ambiguity, I put the constant term first and then the log afterwards. That way there's no mistaking what number is going inside the logarithm and what number is not. You also, I said, could rewrite this as log base 10, so you could explicitly write out the base if you felt like it, but not required, because we all should understand that log with no base written down is log base 10, that is the common log. So for this, the solution would just be the single point, the single value of x, 3 plus log base 10 of 7. And again, this is the exact value. So if you were to grab your calculator and find out what is log of 7 plus 3, and you were to run that through your calculator and say, oh, the answer is about 3.8 something or other, that would again be an approximate value, which is not what we're interested in. This would be the exact solution. This would be the exact value.